So in last session, if you remember, we started plane curvilinear motion in 2 dimensions. Now our particle is moving in 2 dimensions simultaneously. So we discussed how we will be actually defining the position, velocity and acceleration for a particle which is undergoing plane curvilinear motion, right? And then we discussed that there are 3 ways we can describe such a motion. One is using rectangular coordinates, one is using the normal and tangential coordinates, and then also using polar coordinates. We discussed the use of rectangular coordinates to describe a 2-dimensional motion, which essentially summarizes into that we will decompose a 2-dimensional plane motion into the x and y components, and then we can convert the displacement, velocity and acceleration into each other by treating x component separately and y component separately. So one special application of this 2-dimensional kinematic theory is projectile motion. So once we are able to describe the curvilinear motion using rectangular coordinates, we can apply this whole concept to a type of motion called projectile motion. We discussed that today, right? And then in the next session, I will be describing the same plane curvilinear motion in another coordinate system called NT, normal and tangential coordinate system, NT coordinate system. And then in the next week, we will discuss how we can describe the same motion using polar coordinates, right? So in last session, we discussed how we can describe the position of a particular point which is undergoing a 2-dimensional plane curvilinear motion. Actually, we will be using a position vector to describe the location, right? Similarly, we will be using a velocity vector to describe the velocity of a particle which is moving in a curved path. So v vector is actually the instantaneous velocity vector. It is the first derivative of position vector with respect to time. We also discussed the vector notation for all 3 quantities r, v and a. Similarly, acceleration was the first derivative of velocity vector with respect to time. An important point to consider was that the velocity is having a direction tangent to the path of particle, and acceleration have a direction same as the delta v or change in the velocity between any time delta t. So velocity is directed in the direction of delta r, which will actually become tangent to the particle when you apply the limit delta t approach to 0, but acceleration will neither be tangent nor normal to the path. Actually, it will be tangent to another line called hodograph, which we can obtain by starting the velocity vectors from this common origin point at different time instants, and then we can join their tips to get that hodograph. Acceleration will be tangent to that particular line or curve, not to the actual path. Then we discussed that there can be 3 ways we can describe this kind of a motion. The first is rectangular coordinate system, a coordinate system which is represented generally by x, y, where x and y are 2 perpendicular axes, and we can divide any vector, plane vector into a summation of x coordinate and y coordinate, a component along x and a component along y. Similarly, we will be discussing in next session the normal tangential coordinate system or NT coordinate system, and then also polar coordinate system. In the rectangular coordinate system, we actually started with these 3 equations. A position vector r can be written as a sum of its x component and y component. The x and y quantities, scalar quantities, are the magnitudes of the x and y components of r respectively, and I and j represents the directions of the x and y components respectively. I and j are the unit vectors. When we take the derivative of r vector with respect to time, we get the second equation, which tells us that velocity also have two components along I and along j, and the magnitudes of those components are simply the first derivatives of x and y respectively, right? So we can convert x to x dot, y to y dot by taking first derivative with respect to time, and then we can separately determine the x component, magnitude of x component of velocity at any time, and magnitude of y component of velocity at any time. We can take that derivative one more time and determine the x and y components of acceleration, actually the magnitudes of x and y components of acceleration represented by x double dot and y double dot, right? So these three equations tell us that if x and y are given as a function of time, x and y, we can separately determine the velocity x component and y component, and accelerations x component and y component, right? So if I represent x dot with v sub x, y dot with v sub y, we can say that at any time instant the magnitude of velocity vector or length of the velocity vector will be this much, right? And that vector will be making an angle theta with x-axis, which can be determined using this second equation. Same, we can describe acceleration as a sum of its x component and y component, and the acceleration magnitude at any time instant t will be this much, where a sub x is the double derivative of x and a sub y is the double derivative of y, right? So a sub x is actually x dot dot and a sub y is y dot dot. Similarly, v sub x is actually x dot and v sub y is actually y dot, right? So towards the end, we discussed what kinds of problem you may expect in this particular chapter. The first was that if x is given to you separately as a function of time, y is given to you separately as a function of time, and you are asked to determine velocity and acceleration at any given time. So what you should do? You should take its first derivative with respect to time, y also dy by dt will become y dot. So x dot and y dot are simply the x and y components of the velocity. So at whatever time instant you are asked to determine velocity, put t equal to that number in the relationships, and then you get the v sub x and v sub y. So this x dot is actually v sub x, this y dot is actually v sub y. So you can apply the same equation which you have seen in the last slide, this one. So you know x dot, x and y dot, you can calculate v also. Same, you can determine acceleration also by differentiating one more time. So you get x double dot, y double dot, you can put any value of t in their relations to determine the x component of acceleration a sub x and y component of acceleration a sub y, right? And finally you can write a as a sub x times I vector plus a sub y times j vector if you are asked to determine acceleration vector. If you are asked to determine the magnitude of acceleration vector, then it will be square root of a sub x square plus a sub y square. Similarly, you may also have another type of problems in which acceleration is given to you separately for x component and y component, and then you are asked to determine like v or r, right? So obviously in this case you will integrate that acceleration for x separately, for y separately, to determine the x and y components of velocity. You can carry out that integration one more time to determine the x and y components of the position vector. So once you have x and y, you can write r as x times I plus y times j, right? Similarly, you can write v as vx times I plus vy times j, right? And one common type of question in both categories would be to plot the path, which essentially means that you should write x as a function of y or y as a function of x. So if for example acceleration is given, you have to integrate two times to get x and y, and then plot y as a function of x. That plot will be actually the plot of the path which the particle moved, right? Similarly, in here also you can be asked to plot the path by directly giving x and y as functions of time. The takeaway from all that discussion was that we can consider a curvilinear motion as a sum of two simultaneous rectilinear motions, one is in x, one is in y. When we describe a curvilinear motion in terms of rectangular coordinate system, right? So the whole summary is this, that rectangular coordinate system gives us an opportunity to describe a curvilinear motion as a sum of two simultaneous rectilinear motions. We can treat those two motions separately and then we can combine them at any time instant to exactly reproduce the same curvilinear motion. Now, one important application of this two-dimensional kinematic theory is projectile motion. So, it is an application of 2D kinematic theory. We will apply whatever we have discussed up till now to a case when a particular particle started its motion with some given initial velocity v naught at one particular starting time, and then it followed a curved path which is represented by the orange color here. So this orange dotted line is the path of the particle, right? And then it again came to an impact point on x-axis. So if x-axis represents the ground level and y represents the height axis, then projectile motion becomes a special case of curvilinear motion, right? So particle is actually following a curved path in an xy plane, but xy plane is now what? Y is the height axis now, and x-axis can be the direction of the projectile motion, right? And that projectile will have some initial velocity represented by v sub o or v naught, and then it will actually follow this curved path. Now, if we ignore aerodynamic drag, air resistance, if we ignore the curvature of Earth, like we assume that x is perfectly horizontal axis, if we ignore the rotation of Earth, the effect of rotation of Earth, if we assume that the effect of height on gravitational acceleration is negligible, so we ignore the effect of height also, with all those assumptions, we can actually treat this motion as a constant acceleration case. And if you look closely, since the velocity have some angle theta with horizontal axis or ground axis having some initial value v naught, if you look at the acceleration components in both directions, we will obviously not reference the force which produced that motion initially in the first place, because we are discussing only the geometry of motion, kinematics. So once that motion started with initial velocity v naught, the only force which is acting on our particle throughout that curved path is the gravitational force, right? There is no horizontal force applied to our particle. We only have a vertical downward force, which is gravitational force, which is the only force, and the particle is moving under only that force, right? So throughout that path, throughout that orange line, the x component of acceleration should be 0 because there is no horizontal x direction force applied. Gravity do not have any x component, right? However, the y direction acceleration will remain constant, equal to minus g, if minus represents a downward direction, and g's will be simply 9.81 meter per second square or 32.2 feet per second square. It remains constant throughout that orange path, right? But again, this is with assumption that there is no air resistance, there is no effect of curvature or height, right? And similarly, the effect of rotation is ignored. Then the g will remain constant throughout the flight, but there is no x force resulting, really there is no x direction acceleration, right? So if I want to know the acceleration of that particle at any time instant along the orange path, the x component of that acceleration should be 0, but y component of that acceleration should be minus g, right? Which means that we can separately treat x and y components of this motion when we describe it in rectangular coordinate system. We can separately treat x and y, but those both cases will be constant acceleration cases, right? In one case the constant acceleration will be 0. In second case that constant acceleration will be minus 9.81 in SI system, right? So everyone is clear why a sub x should be 0 in a ideal projectile motion. Ideal means that we have all these assumptions in place, right? Obviously, ignoring aerodynamic drag will be a very poor assumption in several other cases when you have very high velocities or when you have very light object which is represented by a particle in this problem, right? So imagine a very light ball which is moving in a projectile motion. In that case, ignoring aerodynamic drag will be a very poor assumption, right? In that case, the particle may not follow this perfect curved path, right? So with all those assumptions, a sub x can be considered 0 and a sub y will be minus g. So now it means if this is a constant acceleration case, we can apply those three equations which we derived earlier for constant acceleration of a rectilinear motion, but now we can apply them to x separately, x direction separately and y direction separately, because we have seen that in rectangular coordinates we can consider a curvilinear motion as a sum of two simultaneous rectilinear motions. So if you revise those three equations, it was v is equal to v naught plus at. The second was s is equal to s naught plus v naught t plus 1 over 2 at square, and the third equation was v square is equal to v naught square plus 2a s minus s naught, right? First two we actually derived by integrating acceleration two times, one time to get first equation, one time more to get the second equation, and third equation we actually derived by applying equation 3 directly, v dv is equal to a ds, right? So these three are the equations we used in rectilinear motion for constant acceleration case. Now let's apply them separately to a projectile motion case, x separately, y separately, right? So our launch conditions will be launch speed v naught, initial velocity at origin, launch angle is theta with x-axis, and launch coordinates will be x naught, y naught. So the origin have some coordinates x naught, y naught, right? Conveniently we can assume them 0, 0 for several problems, right? Initial velocity will have two components, vy naught, which will be v naught sine theta, and vx naught, which is v naught times cos theta, right? At any other time instant after initial point, again we will be having two components, vx and vy, but they will be changing depending upon at what stage your projectile is. So exactly at the point of impact, you will be having some v, let's call it like v final, and it also will be having two components, one in this direction, one in this direction. So that will be v, if this is v sub f, then it will be v sub f cos theta and v sub f sin theta, right? So that will be your final velocity or impact velocity, right? So let's apply these three equations to x direction separately. So when I apply these three in x direction, I will put a equal to 0, right? And s will be represented by small x, right? In x direction, I will be representing small x with the distance in x direction. So if you go back in the notation which we discussed, here you can see that small x is the distance in the x direction or magnitude of the x component of the position vector. Similarly, small y is the distance in y direction. So let's keep that notation consistent and apply in x direction separately. When you apply to these three equations to x, first equation will simply, this one becomes 0, here also it will become 0, and the third term will also become 0 because a sub x is 0, right? So v will simply become v naught of x, which is the x component of the initial velocity. So that's why we get the first equation here, v sub x is simply vx0. So it means that throughout the projectile motion, the x component of velocity remained constant and it remained equal to the x component of initial velocity, right? So I go back again and just show you that when I apply the first equation for x direction separately, it will become v sub x, and the second term will become x component of the initial velocity. So we get this first equation when we apply the first equation, this one, in x direction. When we apply it in the y direction, now the acceleration will be equal to minus g, right? So the same first equation will give us this second equation, that is when we apply it in the y direction separately, right? So our first equation is divided into two equations, one in x, one in y, right? Let's apply the second equation now. S is equal to S naught plus V naught t plus 1 over 2 AT square. For x case, the third term will become 0, and we will simply be getting this term x is equal to x naught plus Vx naught times t, right? Third term will become 0. So x is the distance in x-axis is equal to the initial distance x naught, right, from where the projectile started, because this coordinates are x naught, y naught, right? Generally they are 0, 0, but they may not be 0 for certain case. So you will be having x is equal to x naught plus v sub x naught times t. So if I go back, you have v naught t, so which will actually become the x component of v naught times t, plus third term will become 0, right? So you will be getting this equation when you apply the second equation in x separately, and then you will be getting this one when you apply that same equation in y separately, s minus s naught plus v naught t plus 1 over 2 AT square, right? So if I write it here, s is equal to s naught plus v naught t plus 1 over 2 AT square, I apply it to y direction separately. So y direction distance is y direction initial distance is y naught, y direction's velocity, initial velocity will be the y component of velocity, it will become v naught vy naught, actually it will be v naught sine theta times t, and acceleration is minus g, so it will become minus 1 over 2 gt square, right? So we get this second equation. When we apply third equation, which is actually v square is equal to v naught square plus 2a s minus s naught, when we apply it to the third to the x-axis separately, third term will become 0, and we will be simply getting the same first equation again, right? So third equation won't give us a third equation in x separately, it will simply become v sub x is equal to v sub x naught, right? Same as the first equation already we are having. So therefore there is no third equation in x separately, but there will be a third equation in y. We can apply the same equation in y separately, we will be getting vy square plus vy naught square minus 2g times y minus y naught. S minus s naught will become y minus y naught in this case, right? So in short, we will be having these 5 equations which are governing our projectile motion if we invoke all those assumptions like no aerodynamic resistance and no effect of rotation and height on gravity and all that, right? So these 5 equations we will be using in different forms to determine some unknowns for some given knowns of a projectile motion, right? For example, think of a problem where the initial velocity and initial angle is given, and you are asked to determine how much range that projectile will cover, or what is the maximum height the projectile will be having, right? Or you can be asked with the value of velocity at a particular point or a particular state of projectile. So you may be asked that what is the velocity and acceleration when projectile is, let's say, somewhere here. You may also be asked to plot the trajectory of a projectile, right? So there can be several types of questions which you may expect. One thing before we actually start a few problems related to projectile motion is that all the 5 equations, they are only applicable for the case when you ignore aerodynamic drag, right? If, for example, if you want to include the aerodynamic drag in this whole scenario, then the equations won't look that simple, right? They will be complex equations and they will be describing a motion which may not be parabolic, right? Because currently what you can do, using these 2 equations, these 2 x and y, you can eliminate t from these 2 equations and can write y as a function of x, and that will become the equation of path, right? If you do that, for example, if you eliminate t from this equation x and this equation y and determine some y is equal to f of x, you will see that that will be the equation of a parabola, which means that the path will be perfectly parabolic in the case when you are assuming all those assumptions, right? So these assumptions will result in a perfectly parabolic path. But if you invoke the aerodynamic drag, include them in the equations, they won't look like this, and the motion which they will be describing will be non-parabolic, right? So generally the drag force, the aerodynamic resistance, if we represent it with F sub d, that is proportional to the square of velocity. It also depends on the weight of the object. It also depends on the size of the object, right? The bigger the size is, the more air resistance it may experience. The heavier the weight is, the lesser will be the effect of air resistance, right? But mainly it depends on velocity of the projectile and square of the velocity in most of the cases, right? With this information, can someone relate it with a problem which we discussed in last class, in which you were given acceleration as a function of velocity? A was minus k v square, if you remember. That problem was talking about a ship moving in water, a freight moving in water, and that motion was experiencing a negative acceleration or retarding acceleration. Obviously should have been produced by a retarding force on that ship, but that retarding acceleration was proportional to v square, right? Now we are talking about a projectile which is moving in air, right? In that case it was a ship moving in water, right? Can someone relate a common thing between both of these cases? What is common between moving in water or on water and moving in air? What is common between water and air? They are fluids actually, right? They have a property called viscosity, and the property viscosity actually is responsible for applying a resisting force whenever an object, a solid object, is trying to move through them, right? So in that case, ship was experiencing a resisting force, resultingly a resisting acceleration or retardation, which was proportional to v square, right? And now I am also telling you that when something is moving in air and you want to introduce the drag into the equations of motions, that drag force is generally proportional to the square of velocity. So faster the object is moving, projectile is moving, more the drag it should experience, right? Same is the case with that ship also. This equation is telling you the faster the v is, the faster that ship is moving, the more retardation it should experience following this relationship, right? Actually, it's the property of all viscous fluids. We call them viscous fluids. And this property simply says that the resisting force which they would offer to your particle or your object which is moving through them will be mostly proportional to velocity. In many cases, velocity scale, right? For example, one example from civil engineering I can give you. Civil engineers, they design high-rise buildings against different kinds of loadings, and one of such loading is wind loading. So for example, if you have a skyscraper standing like this, it will be experiencing wind load, which is a horizontal force applied to the outer surface, right? And the wind forces, if I call them F, they are proportional to how fast the wind is blowing, right? So generally that F is proportional to V square, where V is the velocity of wind, right? Obviously this F depends on other factors like how big the structure is, how much size of the facade of that building is, whether that outer surface is an open surface or is closed all around and all that. But mainly that force would depend on scale of the velocity. So it's like the structure is standing in moving air. It becomes the same case when you have an object wants to move through a particular fluid, right? So in that case, please keep in mind that our perfect parabolic shape will not be there. Our equations of motion won't be those 5 equations, right? So whenever we have, for example, larger velocities, larger values of v, right? And similarly, lighter objects being represented by our particle, right? And similarly, for example, when the projectile has a so high range that the effect of rotation of Earth need to be considered, right? So maybe high ranges of projectile, right? And similarly, the projectile height is also sometimes becomes so significant that the value of g doesn't remain constant. In all such cases, for example, very high heights. Similarly, variable density of air. These are all the things which are not included currently in our mathematical model represented by those 5 equations. If any of these factors become significant, then we need to explicitly account it in our calculations, and in that case we will be having a non-parabolic trajectory of a projectile, and it will be actually described by very complex equations, right? So those complex equations may not be easily integrated. For example, if I give you some a sub x, some a sub y, which is very complex, then it may not be simply integrated to determine the velocity x component and velocity y component. So in those cases, you may need to invoke numerical integration methods. It is generally suitable for all those cases where you cannot simply perform the classical or analytical integration. The function is itself very complex, or it may also be described numerically sometimes. So imagine that a sub x or a sub y is not given to you as a function, but numerically given to you, like the value of a sub x for different time intervals, similarly for a sub y for different time intervals. Then you would opt for numerical integration. So we will be discussing mainly the projectile motion by invoking all those assumptions, which means we will be mainly using these 5 equations, right? Let's now quickly solve a couple of problems in this area, and I selected representative problems which will cover several types of calculation. So in projectile motion, you can expect problems. For example, first type can be that find the maximum height which a projectile reaches. So for example, in x and y, one problem type can be that determine this height small h, right? Find the maximum range or distance covered by a projectile. So determine this horizontal distance, the complete range which that projectile covered. And by the way, what would be the solution approach for both of these cases? You know that for maximum height, what happens? V sub y becomes 0, right? V sub y becomes 0. So we can use this information in our those 5 equations to determine small h, right? So actually it becomes a problem of determine y when v sub y is 0, right? So I can rephrase this first line as what would be the value of small y, because what is x and y? They are the positions of this projectile at different time instants. So what will be the small y when Vy is 0? So this information, when you take it to the 5 equations, you can solve for this h. H is actually that value of y coordinate when Vy became 0 for that particular instant. So at the maximum point at apex, Vy became 0, right? V sub y. Similarly, when I say determine the maximum range, it is I am actually asking determine the value of small x throughout the projectile, right? So if, for example, the projectile takes t sub f duration of whole projectile, right? Then I am actually asking determine x when t is equal to t sub f, right? So actually for the second case, you need to first determine what is the value of t sub f, like the complete duration of the projectile, and at that particular instant when t is equal to t sub f, what is the value of x? That is the whole x range. Now how to determine t sub f? T sub f will be a time when y is 0, right? Because at t sub f your projectile is here, so y again became 0, right? So you can, if y is given to you as a function of time, put it equal to 0 to get t, right? And that t is your whole duration for which the projectile moved. Put that t in x as a function of time to determine the range of the projectile, right? So please note that while I am saying it, this is what this equation x is an x described as a function of time. Similarly, this is y described as a function of time. You can put y equal to 0 to get t. That t will be actually your whole duration of the projectile. Similarly, you can be given with let's say some values of velocity at different time instants, or maybe the impact velocity, but asked to determine launch speed. In the first two cases, obviously initial velocity or launch speed should be given to you, right? And the angle also should be given to you. But there can be a third type of question when you are asked to determine launch speed or launch angle also. So V0 and theta can also be your unknowns, but obviously some other information need to be given in that case. And then the final two questions is that at any time during the flight, I can ask the x, y coordinates, like what is, for example, here, what is x and y? Or I can say that, okay, when it was here, what will be the velocity v vector? You may be asked to determine velocity at any time, maybe at here, right? So v vector can be one of your unknowns. So how you would be determining? You would be determining Vx separately, right? You have an equation. Vy separately, you have an equation. And then finally writing the V vector as V sub x times I plus Vy times j. But that can only be done at a given time, right? At some particular time, at some value of t, right? So they may ask you to determine for example, what will be the velocity or what will be the position at a given time. So all 5 equations will be applied in different arrangements and different orders also, depending upon what is given, what is to be determined. So please try to again classify the types of problem in projectile motion case.